Thank you for joining us. We're going to go over the base plate program for steel columns now. And we'll go ahead and add one of those calculations to our project. This is a rather simple program, but we'll go through it in as much detail as needed. We open up the program and we have our General tab and Materials tab. Notice that we can do base plates with analysis of either ASD or LRFD analysis. Depending upon which analysis you choose, for ASD we do still provide an allowable stress increase factor. I don't believe that's allowed at all in the 13th edition AISC, but this program, the method spans several codes, so we allow you to do that. Here's the omega factor for 13th edition AISC. We do let you modify that for the concrete portion of it. We also allow you to decide whether you want to have the program calculate F sub P, or you want to just be able to enter in the nominal bearing capacity yourself for the concrete. Over here we have a selection between how to consider bearing. If we say full bearing, I believe that's a little bit more conservative than partial bearing. You can read the description here. This is really tied back to the AISC design guide and their recommendations, so I would recommend you becoming familiar with that. Let's skip over to load combinations just because it's always the same. We do have the ability to use those allowable bearing increase factor, allowable stress increase factor for each load combination if you want to. By default, they're not checked. Column specification, we can press this button and basically pull in a standard column section for use. We have the some important section properties from that section. If you want to edit those properties, something special, you can use this little feature and it'll modify the section properties of the standard AISC section. Let's get a sketch going here. I've got a 10 by 45, a little cramped, so let's pull the length of that plate out to about 18 inches, and the width is about right. This is a casual session here. We're just throwing some numbers in just to show you how the sizing works. There's the base plate size, concrete support size. We can do 24 by 24. You can see we have the concrete area drawn around the base plate, and then the concrete area is used for the bearing increase because of the proportion of this. By the way, we use not a projected bearing area. We use a similar ratio bearing area, and so here we have this projection past the end of the plate, and we use a proportional projection around the side of the plate. And if this is way out here, that's 36 inches, and let's make it 48 inches. We're not going to use the area of the tips of this. It's going to be proportional square area. Let's get that back to 24 by 24. Applied loads, we can have dead load, we can have axial loads, we can have shear loads, and moment loads. The program is very flexible, and it can do various states of bending on the base plate. Let's just do 24 kips dead load and 14 kips live load. We have results down here. This is a table where you actually select which load combination has been run, so you can see the detailed results of each and overall results. So what the program is telling us now is that we're using allowable stress design. The load combination that creates the highest stress level is dead plus live plus earth, which is not used, but that's just the way the load combination is. We have axial load only. This is our plate size that we've entered, and here's all our ratios. What we need to do is put a moment in here. So let's put in an earthquake moment of 12 kip feet. All of a sudden we have some more load combination as you can see here. we're clicking on the dead load plus earthquake load combination. You'll notice that it's telling us that axial load plus moment is the case because we have moment now. The current distance is less than the eccentricity, is less than half the base plate length. So that means that the moment is high enough so that we have a triangular soil pressure diagram under the plate. If we take this down to 4, we're probably going to see that the eccentricity is less than L/6. So there's various regions that the program designs for. As you know, when the eccentricity is L/6, the base plate is in pure compression. It is a trapezoidal loading under the base plate. If we kick this up to 12 kip feet, there's a lot more moment on it, and you'll start getting triangular pressure. We still don't have any anchor bolt forces yet. Let's kick it all the way up to 34 kip feet. Now we're getting anchor bolts. Okay, there's a lot of moment. The eccentricity is way out there. We have tension on our bolts, and here we start having bolt information. There's no values here because I haven't entered in anything for anchor bolts yet. I'm just going to put in some arbitrary values, and then we can see tension per bolt, anchor bolt allowable is this. There's our ratios. So going down and looking at this, we have our overall governing condition here, which is showing us that it's dead plus 0.7 E is our governing condition. We have a state where the bearing stress exceeds the allowable, or the bending stress exceeds allowable, excuse me. So in this case, we simply go up here and kick the thickness up a little bit, and there are stress ratios in. Let me do that again. You'll notice I'm clicking the spin button up here in the thickness, and we're getting that plate to work. Okay, so that gives you a lot of information about the states of stress in the plate for all different conditions of loading and different eccentricity cases because of the applied moment, and how it's stabilized by dead loads and how they affect the load factors. There's our sketch, and that's about it for this program. Thank you for joining us, and remember, support intercalc.com for any further questions.